Hi friends, today we will see how to model the pipe where we have left yesterday. We'll continue the modeling. So we have completed till this support yesterday. That's 500. Okay. Yeah. From here we will start. So the line is continuing in Z direction. Just you copy this and paste it here for better understanding. Okay. So line is continuing in Z direction. So what is the dimension? 350. So 350 we have one branch connection and 650. Today I will go a little bit fast to complete the modeling. So here 350. Sorry. And then we'll do it or support anything, whatever it is given in the material specification, you have to update. And then 650. After that, 650 is the go to next element. 650, and one branch connection is the where to define 670 is this you can consider as vector. After that, 700 is there, including the flange thickness. So you have to subtract the value from 700. What we'll do minus, we know the flange dimension is 112 plus 700. You will get the pipe dimension. Okay. So after that, you need to model the flange. 112. And you have to enter the weight as 389. You have to double click the rigid, and again one more flange is the rigid 389. Okay. Then again one support is there, that is at 400. 400 means 400 minus 112, that flange thickness. So minus 112 plus 400. Sorry, minus 112 plus 400. Okay, so if I got one thing yesterday, so here some for bends and flanges and other valves and all will have different materials. So we are not entering the material for the valves, flanges, and other fittings. Okay, for the elbows and all. So what we are using, we are going with the pipe material only. So only we are changing pipe material. We are not going to use any flange or any fitting material, because if you see or fitting material is A105. Those are all forged material. Flange material is 105, A105. So all will have different material. So we are not going to change anything. Just we will use pipe material only, because we are doing piping flexibility analysis only. So based on the pipe material and temperature, your expansion and contraction will occur. Okay. So please concentrate only on the pipe material. You have to change only the pipe material. And one more thing, you need to define the global coordinates. Yesterday I told you in this isometrics we don't have, they didn't provide any global coordinates, but you have to provide global coordinates. Here you see this is global coordinates, V or set. See, this is global coordinates. So you can give at any point of time, but at the first node, if you provide, then it would be easy. Or if you complete the modeling, you can give the global coordinates. So global coordinates is very important for one is for the wind. I told you yesterday, wind, if you use wind pressure versus elevation, then this global coordinates only will decide the wind elevation. Okay, so it will take this elevation and it will be considered in the analysis. If you are not specify the global coordinates as correctly, then wind will be specified in a different elevation. Okay, so it will not match. So you have to enter the global coordinates first for to get the correct results of the for the wind cases or the occasional cases. And second thing is to check the model. Whatever model we have done, whether it is correct or not, we don't know. So if you want to ensure the model is correct or not, so we need to provide the coordinates. For example, if you check this one, so this is a first node at 10. They have provided some coordinates, east, north, and elevation. These coordinates has to be entered at the first node, and you can check the coordinates where the next coordinates has been provided. You see, here they given these coordinates after this T. So you can check the coordinates in CAESAR. It should match. You no need to provide for all the locations. At one location, you have to give the global coordinate. So automatically it will be calculated, and you can check the global coordinates at this particular T location. It should match. If any mismatch is there between the isometric drawings and the 3D, CAESAR model, then our modeling may be wrong. So you can correct. Okay, so you can check the modeling correctness in this way. Okay, so you have to define the global coordinates. I will show you after some time. Okay, so these 2 points I missed out yesterday. Okay, and then here 288, that is 400. No, 400 on support is the restraint. Restraint, you double click the restraint and support it will be appearing, and plus y you have to give, and then again it is 900, 500. So I'm leaving like this. I will add this, and or I will just give 900, 900, 500, and then again 500 with flange. So minus 112 plus 500. You see, whatever model it will be appearing here, and then 112, that is flange 389. So since I know the value of this flange and dimension, I am just entering. So you have to refer each and every time. If the line size remains same, okay, then you can enter the same way. But if the line size, if the line size changed, or I mean any spec break is there, or if any rating changes, then you have to refer the pipe cut approve and get the correct value. Okay, and 513, that is valve dimension. So yesterday we have modeled one valve for this size. So I will take the value from that. You see here, or you have to refer the pipe cut approve. Since there is no time, what I am doing, I am copying this one and I will paste it here. Okay. Then go to the next element. You will have flange once again. 389. Okay, so it is continuing in the next sheet, that is sheet number 7. So sheet number 7 is here, and we have model up to here, you say. And after that, on support is that is at node dimension 500. So what we need to, you need to subtract this flange length plus 500. So on support is there, you select here. So these supports are very important. I mean, if they are not provided support also, after analysis, you can suggest you have to add the support after the valve. Okay. So better for 8-inch or 10-inch above lines. Before and after the valve, you have to provide on support. That is the correct procedure. For example, like this. Any valve 10-inch, okay. You have to provide the support before and after the valve with the dimension of maybe around 500 mm or 1 meter. 1 meter. Okay, so like this. So please keep in mind, because in CAESAR it will not show any failure and all, but we have seen so many sites what happened this, we have not considered properly the weight of the valve. So what happens? This line will sag. like this. So this valve, there is a failure at the valve location. Okay, at side, if you see, there will be a bend. There will, I mean, the deflection is more at this location. I will tell you later that one. Okay, and then after that 500 mm is the after this support. After that 1580. I will not model this. I am not defining the shifts and T's. You have to define the shifts and T's wherever branches are there. 1580. So 1580, one flange is there. Okay. So minus 112 plus 1580. Oh, sorry. Minus 112 plus 1580. That is 1468. So after that, on set of flange, that is 112 rigid 389. So again one more flange 112 389. Okay, so now you see, so here up to here we have model. Okay, so after that you see the same one spool is there, again two flanges, again on spool is there, two flanges. So instead of modeling one by one, you can do, I mean, each element you can model like this, what now we have followed. Or you can copy this and you can check. I mean, you can copy and paste also. I will show how to copy and paste. Okay. So here you can select like this, so this portion only. You can select like this and duplicate. You can do like this also. Okay. Or go to this. This is list input and elements. In this, say 1690. 1690 to 1750. So whatever it's selected, highlighted in yellow color. So you can give a right click, block operation, duplicate. So duplicate means it will show identical mirror and other things. And at the end of the input, 1 minute. 1 minute. Sorry. List input elements. So 1690 to 1750. Yeah, this got selected. Right click, block operation, duplicate. Okay, so like this it is there. So you can I think there will be a three options, but here it's showing one option. 1 minute, I will check the other node numbers. Block operation, duplicate. You see. So these three options will be there. So it means at the end of the current block means after 16 node number 1610 it will be pasted. Whatever we are copying, that will be pasted after 1610. At the end of the input means after node number 1750. That is the last element. After the last element, it will get pasted. And after element 1610 means it is same like at the end of the current block. Okay. So you have to select in a correct manner. Okay. If you want to insert any element after 1610, so you can paste it there. Okay. So now we are going to copy this one on. Right click, block operation, duplicate. You will see. So at the end of the current block or at the end of the input, these three options will be same only. So now what we need to do, anyway this node number will be continuing from 1750 only. So the next node should be start from 1750. So what we need to do, we need to add this 1690 plus 60, then you will get 1750, correct, no? The node increment means that one only, plus 60, 1690 plus 60, then it will be continuing, okay? So what we are going to give, just give OK, plus 60, you see, another set of pipe with flanges pasted here. So again, what I am going to do is select this one, lock operation, duplicate, and again you give 60. So again one more set of pipe with flanges will be pasted there. You see, again it is pasted. So now we know up to here we have model. So here we need to check the dimensions as per the isometric drawings. So the dimension from, you see, the flanges is, between the flanges is 1400. So how to measure this one? So to measure the dimensions between different elements, one option is there, you see on the left side, distance, one option is there, distance, okay. So here you select distance, not this one, distance, and you have to check the node number, which node number to which node number you want the distance. Ours is 17302 to 1790. So you select distance 17302 to 1790. You see the dimension is 1692. So what should be your dimension? Your dimension, what is the dimension required? 1400. Okay, that means you have to change the dimension 1400. 1692 minus 1400. 292 mm you have to reduce. So here you need to reduce 2 minus 292 plus. Okay. So now you can check the dimensions between 1730 to 1790. That is, you see the dimension is 1400. So that is correct. Okay, or you can check like this also. Manually you can check. You have to select here one. So you go to top view to get the correct. So you measure this. You see one circle is there, no red color bubble. You select there, and here also the same thing. See, it is 1500. Wherever it's required, you can measure. So likewise, you need to change this dimension. So this is how much the total dimension is? 1760 plus 1900. 3660. Total dimension is 3660. Out of that, you have to subtract the flange, two flanges, 112 minus 112. 3436. So the overall dimension, it should be here 3436. 3436. Okay, so if you want to check the dimension, you check from 1790 to 1850. 1790 to 1850. So the dimension is 3660. So overall dimension is 3660. Okay. So in between one support is there, where from this flange to this support is 1900. That means 1900 minus the flange dimension, flange thickness, 1780. So what we need to do, we are going to break the element. These are two elements. Control B, and what is the dimension? 1788. So here, CAESAR always how it will show, no, it will break the, if you are going to break the element using single node, it will show the midpoint only, means the center of 3436 divided by 2, it will give 1718. So don't believe in the dimension from CAESAR, you have to provide the dimension as per the isometric drawings, whatever dimensions provided. It should be 1788. And if you know the support node number, you can enter the support node number that yesterday we have seen, no? Yeah, okay. So it will take the support node number from 1090. Already we have defined the support there. So whatever support defined at node number 1090, it will be appearing here. You have to be correct, okay? So then again one set of flange. So that I think we have model, no? Yeah, and after that one elbow is there, bend is there, 416 at 416. So not exactly 416. You have to subtract the flange dimension, and you have to define bend. So actually, what is the dimension for elbow length, elbow arm length? It is 1.5D, no? So 1.5D means 8 into 25.4 into 1.5. So the dimension should be 305. So you change this one to 305. Okay, 1 mm only, not one issue. Okay, then you see again the pipe is going in a different direction. So I am pasting this. So it is in Z direction, and now the direction has been changed to minus X. The pipe is traveling in minus X direction. See, correct? No, this is plus X, and pipe is traveling in this direction, minus X. So go to the next element. So minus 2000. So 2000 on support is there. So okay. So after this, a lot of flanges are there. So I'm not going to model anything. Just I will enter the dimensions and will try to close. Next is 1200. After that, minus 1200. 3630 minus 3630 minus 378. You see. So 378 on support is there. You just define the support. I have not modeled the flanges and all. You model, you practice as per your isometric drawings. After that, 2800. 2800. So in the 2800, you have one bend. After that, again it is going in plus Z direction. So go to the next element, and in plus Z direction 416. Dimension is minus 112 plus 416. So on flange is okay. You see here, I forgot it. So here, I told you, no, but for bends, if any flanges are coming, you need to change it to single flange. Okay. So single flange, if one more set of flanges coming here means, then you have to give double flange. Okay. So here what means, this long radius is 1.5D and short radius is 1D, and 3D, 5D bends for pipeline we used to provide. Okay. I will show later. So go to the next element. Flange and then valve is there. Okay. Flange and valve. Well, just I am giving some weight, so you need to refer your isometric and pipe data pro to enter the correct values. 112, 112, not 1120, 89. Okay. So again, the line is getting continued to the next sheet. It is continuing in sheet 8. So it is from sheet 7 it is coming. So we have model up to the flange. After that, after the flange on support is there, that is at no at the dimension of 500. Okay, go to the next node. At 500, you enter the support. After that, 7,000, 1,000 plus 6,000, 7,000. 7,000, you have one more support. Then go to the next node. Again, 7,000, one more support is there. 7,000, one more support. After that, 1493 is there, you see. 1493 in Z direction. 1493. So here you have bend. So here bend is there. So after that, after 1493, it is going in, there is a offset. I mean, line is skewed. Okay. So we need to see in which direction it is going. So it should have traveled in this direction. Means it should have continued in plus Z direction. You see, this is plus Z, and it should have gone minus X direction. You see, the skew is like this. Skew you have to understand properly, then only you will get a correct result. Okay. So this horizontal skew, this is horizontal. If it is vertical skew means the hatch should have been in the vertical. Okay, this you have to see properly the hatch. So it is in horizontal direction. So line should have traveled in Z as well as in minus X. So we know the dimensions of Z, and Z is 3621 and in X is 1500, that is minus X. So you have to give both value here, because since this is not 45 degree, we have different values. If it is 45 degree means both values remain same. So using trigonometry function, you can find the value. I mean, using sine theta opposite side by hypotenuse, you will get the value. Okay. Or cos theta, anything you can check. Okay. So go to the next element. We have defined the bend. After that, 3621 1500. 3621 in Z direction and 1000 minus 1500 in X direction. You see, you got the pipe, okay, in different direction. So again, what happened? The line is traveling in Z direction. On bend is there, so you have to define bend here, and then line is traveling in Z direction, 2386 plus X plus Z direction, 2386. Here we have a support plus Y, okay. Then again the line is traveling the same direction, plus Z, 1614. Go to the next element, 1614. Again bend is there. Save this one. Frequently you have to save whatever modeling you are doing. Okay. Then you see here, here the bend is not 1.5D or long radius something. It is given as 30D bend, cold bend. Okay, 30D cold bend. So this is for the pipeline. Generally for the pipeline they will use 5D bends, cold 30D bends, elastic bends like 80D, 100D like that. Okay. So that is to provide flexibility for the piping and okay. So 30D bend, we need to define 30D. 30D is nothing but whatever dimension, 8 inch. D is diameter of the pipe. So 30 into diameter. Diameter means 219.1 or 219. You can say 219. 219 into 30. 6570. That is the radius of the bend. So how to define this one? So you see they given typical. That means all four bends are 30D bends. This bend, this one, this one, this one. All 4 bends are 30D bends. So we need to change the bends. How to change the bend? So you select this one. So that's what you need to study the isometric properly. You can change at any time, but if you study the isometric properly, then at the initial stage itself you can correct. Otherwise, you will forget. Okay. Long. So here we have options of long, short, 3D, 5D. There is no option for the 30D bend. So what we need to do in the radius, you can directly type the radius 6570. 6570. Okay, how you see now how smooth it has been changed because your radius is more, no? So based on the radius, the pipe bend has been changed, and here also 6570. Again here also 6570. Okay. Then next note, from year to year. Year to year, the line is traveling in this direction, so it is traveling in plus Z direction, and it should have traveled in plus X direction. So plus Z and plus X. Okay, don't get confused. So don't consider like this direction minus Z minus X minus Z. So from where we are coming, that direction only you have to select. Don't go in the opposite direction. So we have started model from this way here. That's why we are considering plus Z and plus X. For example, if we have started model from here, then you should have considered minus X and minus Z. Okay, understood, no? So here we need to enter plus Z and plus X. So the dimension already we know 3621,500. Go to the next node. 3621 and 1500. You see. So the overall dimension is 3919. That is 3920. So it's almost same only. Okay. 1 mm difference is there, no issue. Then you have pipe support at 1654. 1654. Okay, go to the next element. And if you are going to the next element, don't enter the value in the length. You see, if you double click this arrow after the diameter, if you double click this arrow, here the dimension, here the double click this, you will get this one. Okay. So don't enter the dimension here, you enter the dimension in this direction. It is Z 1654. So 1654, and then the restraint, please select plus Y, and then 5600, 5000. 2 supports are there. Model that one also. 5600, and one support is there. Plus Y, and 5000. One more support is there. So here see we have not defined the bend here, so you need to define the bend, and it should be 6570 the radius. That's what you have to check properly. CAESAR will not show any error. Okay, if you want to reset the weave, reset weave means you can go like this, reset weave. Or reset plot. If you want to reset the plot, you can reset like this. Okay. Or if you want to see any again reset means the south is isometric. If you select this one, it will be reset. Okay. It will get reset. Go to the next element up to 5000 VA model. Then 3468. Again the dimension it's in plus Z direction. 3468. Again the bend is so you have to switch off this one, otherwise automatically it will go to the reset view. You see this is not highlighted. If you highlight this one, what happens? If you zoom here or enter any, you are changing. So what happens? It will go to the original view. So switch off this one. Okay. So here 3468. So after this, what happened is, say, again there is a skew. Again the pipe is having some offset. So again it is going in plus z direction. You see, it is going. It should have gone in plus z and plus x. So since the dimension they have not provided, this is a 45-degree elbow. See the 45-degree bend only. Then your both dimensions will be same only. So we don't know the value, so we will add up this the diagonal value 7360 plus 3900. So the overall dimension of this pipe is 11260. So go to the next element. So since we don't know the dimensions, so what we need to do, already we have done some 45-degree. You go there. This is a 45-degree. Just select any one dimension, any dimensions. You you select, double click this. You will get the dimension. You see x and z are all same. Okay. So you see the cosine values, cos x, cos y, cos z. So we have not provided any value in y direction. That's why it is 0. Okay. And we have provided value in x and z direction. This value is your cos 45-degree. If you cos 45-degree, what is cos 45-degree? 1 by 2, or you need to check. So that's value only it is showing, because we have 45-degree, no? We have 45-degree elbow. Okay. So any 45-degree value, it should be in 0.707 only. Either it will be in negative direction or positive direction. Since a line is traveling in both in the positive direction x and z, it is showing in positive. If anything is negative, then it will be in negative direction. Okay. So here we see what we are going to do. Since we don't know the value of this, we will enter the value overall dimension. Oh, sorry. 7360 plus 3900, 11260. We enter this diagonal value here, 11260. So because your previous node is in z direction, so it automatically it is considering that direction only. So now what we are going to do, we need to change this cosine value 0.707 and z direction as 0.707. You see, this has been changed. So we know the overall value is 11260, and you see automatically the other two direction has been calculated. This is how when the dimensions they are not provided, then you can calculate like this. Or if you have AutoCAD, you can draw and get the value. Okay. And then here one support is there at 7360. You just break this, Control B, and change this dimension to 7360, and we know the node number of support from the previous dimensions. So again, support is created. You select this, select element and select here, double click the bend, change the value to radius 6570, and you see again the line is traveling in z direction. Line is traveling in z direction, that is 3000 on support is there. Go to this one, 3000 on support is there. Okay, you see the line is going in z direction plus y. Again 4000 is the next dimension, 4000. We have to enter the restraint plus y. Again 2114 is there. 2114. So I think this is this line is complete here, because you see this is a fence. So this pipeline is traveling up to the fence. Our battery limit is at this fence only. So the line may be continuing in some other that may be in some other vendor scope. The line may be continuing like this. So what we need to do, we need to consider anchor either here or at this location to fix the boundary condition. So generally in CAESAR for analysis, there should be two boundary conditions, means fixed conditions. One is maybe at the equipment or at the tie-in point. So always boundary condition should be considered. Okay, so the model is complete. Save this one. Up to this isometric we have completed. I will show you the completed model. Previously what we have completed. This one, OIL lines. So here you see, now we have completed the header. After that, one branch connection is there. That is going to PSV, pressure safety valve. Okay. So now we are going to see how to model this branch. Okay. If the lines are interconnected, you can easily model because this T has been defined by us. Okay. So we need to see where the line is getting connected. So go to the, this is a last node number, last sheet, and it is continuing in the next sheet. Yeah, this is the PSV line, PSV inlet line. You see, this is continuing from sheet 6. So you need to see, you need to check sheet 6. So this is sheet 5 maybe. Yeah, it is continuing to sheet 6. This is sheet 6. I am telling means this is sheet 5. It is continuing from sheet 5 and this is sheet 6. See, this is sheet 9. Okay. So this is the branch connection, 3-inch line. So we are going to model from here. So your line number will be changed from here. So we will go to our model. Okay, now we are going to see where it is coming. I think this location. Yeah, at 1450, your branch connection is there. Your PSV is like that. Like this, your PSV should be modeled. Okay, so we will see how to model this one. So we know the branch location. Main pipe is 1450. So 1450, the line is traveling in vertical direction. That is plus Y. The overall dimension is, the line size is 3 inch. The overall dimension is 233. Go to the lowest element. So you remember this node number 1450. Go to the lowest element. I'll see this from node number. It should be your T node number. That is 1450. So I told previously, once you complete one line, that you have to change the series. Means up to 2300 or 400 we have used. So now we'll go with the series of 3000. 3010. And your dimension is 233 in the vertical dimension. And your line number is different line number. See, 3 inch P72556. You have to change this one. P72556. And our spec is same spec only, so you can retain the same. And you need to check the line size, 3 inch. It is 3 inch. So for 3 inch branch, you see 8 by 3. So 8 inches schedule 30 and 3 inches schedule 40. Or you can go to that particular sheet at sheet number 9. You can check what is the line size and thickness. So it is 3 inch schedule 40 A106 grade B. So you have to change this one to diameter to 3 inch, and then weight or schedule you have to change it to 40. You enter 40. And your material remains same only. So what we need to do after that, we go to the line list. Okay. You have to open the line list. So open the line list and check the line number. What is the line number? P722556. Okay, P772556. This is common inlet of RV. This is relief valve. This is not PSV, it is relief valve. So anyway, the modeling remains same only. Whether it is a temperature relief valve or pressure safety valve, so anything, the modeling remains same. So I mean, you need to check this one. You need to. Okay, so now we'll see that the temperature is 82 maximum and minimum is 85 degree. So I mean same only 82 5 already we have defined. Okay, and what about your fluid density? We need to check correctly. Fluid density is also same, and the maximum operating temperature also 55 degree. So everything remains same. So no need to change anything. You just keep this one, and pressure you need to check design pressure, that is 4750. That also remains same. So no need to change anything. But you need to check each and every line. If any line number change or any specification change, then you need to update accordingly. So here all are same only. So we'll retain the same. Okay. Save this one. Go to that particular number ISO. Okay, here 233 we have defined, but one flange is there for the 3-inch flange. You need to check where is that flange? 3-inch 300 rating. Go to flanges, ASME B31.4, well neck flange. Select 3-inch 300 rating. The dimension is 80. So now we have modeled here. We have switch on this T. You just switch off. You see, now we know the dimension is 80 for flange. So you subtract this value, 233 minus 80, 153. So we change this one to 3030 because if you break Control B, then it will show different node number. So I want the series in above 3000. So that's why, and you have to give this value as 153. That is your overload dimension, 153. So next is your flange. So you see 80 mm is your flange dimension, and you have to give the rigid value. That is, you have to calculate the weight, add up the weight, 7.15 plus 3.08, 10.23 kg. We enter here 10.23 into 10 or 9.81, anything. Okay, so one flange is coming. Okay, then, so up to here we have model, then again one flange is the vertical direction. Go to the flange, 80. Again you enter the weight, because already we have entered the weight of this previous one, 102. Rigid, double click the rigid, 102, just enter, okay. And then you see the overall dimension is 172. That means 172 is overall dimension minus the flange length, it is 80. So we'll get 92. But 92 for 3-inch, what is a 1.5D value? Elbow arm length is 3 into 25.4. 4 into 1.5, 114. So you have to enter the value of 114 here, because if you give lesser value, so as per this isometric, if you go, it should be 172 minus 80. Whether we are checking correctly, the dimension is 80, no? So if you enter 92, I will show you what will happen? 92. So one bend, okay. And here flange is there. So select single flange. This side also flange is there, you see. So 165. So again the line is traveling in which direction? I'm copying that one. Caesar axis. For a better understanding only, copying and paste. So line is traveling in, it is going vertical and it is traveling in Z direction, plus Z direction. So 165 minus 80. 165 minus 80. 85 mm. So this is not correct. So it is traveling in Z direction. I have to enter 85. Again, set of flanges over there. Flanges 80 mm. In Z direction, enter 80. Enter the weight. Again 80. Enter the weight. Okay. So here you need to change this because both sides you have flange. No, you have to select double flange. Go to the lowest element. You save this. Okay. So I mean, you can do anything you can go in this direction or in this direction. So I have selected this direction. I am going. Okay. You can go either way. Also. Okay. So I am going this way. Okay. What I will do? So I will model this PSV from here to here. And both are same only, it's typical only. So after that, maybe it is traveling here. Yeah, okay. Okay, so it is going like this. We'll see. So for I'm going this direction plus Z direction. Then you copy this one, 204. 204 minus 80. Minus 80 plus 204. 124. Again one bend, select bend. So again it is going in which direction? Minus Z direction. 700 mm in minus Z direction. Go to 700. 700. Sorry, minus X direction. It is in minus X direction. So again you have to define here as single flange. I didn't mention that one. You have to select single flange. So at 700 you have one support. Restraint plus Y. After that again 300 is there. 300 dimension and one flange is there. You have to subtract that value. Go to the next node. Minus 300 plus the flange dimension is 80. After that you have to model the flange. Minus 80 and then 102. So after the flange one valve is there. That valve 3 and ball valve. So ball valve is 300, 3 inch 300 rating. Go to valve, flange valve, 3 inch 300 rating. So a long pattern or short pattern weight is around long pattern. I am selecting 29 kg. That can multiply 29 kg. And what is the dimension? 290 in minus X direction. 290. It's a 29 kg. 29 into 10, 290. You'll get the weight. Okay, again flange is there. We need to model the flange. Minus 80. 102. And then you see on connection is there, that is at 3 by 2 reducing T, 165. 165. 165 minus 80, you'll get 85. So at 85 minus 85, you have 1 T. So it is a reducing T. Since it's a reducing T, you can select welding T. Whether it is equal T or reducing T, you need to select welding T. Save this one. Again, go to the next node. Again, 165. You subtract the value of flange, and you will get 85 minus 85. Again, flange is the minus 80. Sorry, 102. Okay, and valve is there at 290. So minus 290. And you know the valve weight already we have entered. So I have not defined this valves and all. So you have to do it properly. Okay. Since there is no time, I'm going in a fast way. So you see, since there is a spec break, this line is 31422 or 3. This is in different spec, and the spec has been changed after this flange. This is 36620. The line is continuing in sheet number 10. Sheet number 10 is maybe this one. This is sheet 9. No, okay. That's what. If you have coordinates, you can easily check which sheet and all. So in this project, this is a 2D project. That's why they have not mentioned the coordinates. If it is a 3D means definitely coordinates will be there. Okay. Say. So since there is a spec break, we need to check the flange. 36620. And you see the material itself changed. 36620 material is V423 UNS 08825. And this is stainless steel material. You see 10S, schedule 10S. If any S is there, then it will be a stainless steel only. Schedule 10 means carbon steel. Schedule 10S, schedule 40S, schedule 20S. So it means it is stainless steel. That too, it is, I think, duplex stainless steel maybe. So we see whether this material is available in CAESAR or not. We'll check. Okay. So first we'll see the flange. So this flange, from flange onwards, everything is changed. Since the line number has been changed, we need to check the line list. P72556. So the line number remains same only. Sorry, this spec has been changed. Yeah, this is that one. Yeah, you see. We'll check whether the line number has been changed or not. Yeah, from this the line number has been changed. You see, range P72557. So you need to change from that flange, next flange, no? So the next flange dimension is minus 80, and weight is. So in PSU lines, you should be very careful because inlet will have different pressure and outlet will have different pressure, different material. So modeling should be in a proper way. Then only you will get correct results. Okay. And after this, you need to change the line number. Line number is 3P72557. 72557. Sorry. 36620, no? 36620. I don't have spec for this project. Otherwise, I would have shown the piping material specification. That is very important because For stainless steel, corrosion on it should be 0. You just consider as 0 here, okay? And you need to change the material. What is the material? Pipe material here, from here onwards, it is B423. I think this material will not be there. B423. Ah, it is there. Fortunately, it is there. Okay, B423 UNS 08825. Okay, you have to select this. Yeah, you got it. Okay. But I say the minimum yield strength is not, it's not specified. For example, if you go to this one, you check the list elements. For carbon steel, sorry, you have to select the allowable stress levels. Yeah, you see, carbon steel they mentioned as 241311. This is as per B31.3. Okay, or you can select, you can check ASME section 2 part D for the materials and all. So here in CAESAR, the minimum yield stress is not appearing. So you definitely you have to enter the value, because for hydro test, your stress will be calculated based on the minimum yield strength. That during checking of output, I will tell how it has been checked. Okay. So this value has to be entered. You need to refer section 2 part D or 31.3. Okay. I will tell you later this one. Okay. While doing analysis, I will tell you this one. So here the material has been changed and you need to check the line list. 7, this is that line. Okay. For identification, I'm just placed that line there. I say the temperature remains same, 82.5, and pressure also remains same. And then fluid density 1100, that is remains same, and operating temperature also remains same. So everything remains same, only the material has been changed, and you need to change the thickness. So this is 10s. For 3-inch 10s means you have to give 10s. You see the thickness is very less for carbon steel. Okay. So this SY value we'll take it later. Okay, we'll consider it later. And you save this. Sorry. Okay, so here, yeah. After that, one more support is there. That is 650. So we'll continue the model like this. Minus 650, minus, sorry, minus 650 plus, I mean, you need to subtract the value of the flange length. So here on support is the plus 1. After that again 650 is the 650, again dimension is 650 minus 650, and one bend is the elbow is the. So in piping we'll call bend as elbow, or in pipeline we'll call that one as bend. There are two types, cold bend, hot bend are there. Okay. After that the line is traveling in vertical direction. Okay. It is 193 with valve dimension, with flange. So go to the next node. So we know the flange dimension is 80 plus 193. Okay. And then you need to model the flange. 80 and 102. And then you see, what is that? In between some spectacle blind is there or what? Or there is a change in pressure, I think so. 4430. No, this is pressure indicator. Sorry, leave it. Any spectacle blind is a gasket flange, so there is no spectacle blind. Bursting disc. Okay. A rupture disc is there. Okay, we'll leave like that. So we'll see what is this 90 dimension is there, no? Maybe it is a rupture disc or not, I don't know. Maybe, yeah, BD 72 BD 001. That is they mention as bursting disc. That is nothing but rupture disc. What happens means, this is a relief valve. So in relief valve, in PSV, what will happen means this, because if any high pressure higher than the designated pressure, PSV there will be a set pressure. If it exceeds a set pressure, then it will pop up and it will open. But what happened to the relief valve means they are using this rupture disc. So if any temperature, in order to maintain the temperature for the, pressure for the entire system, if any pressure increases, this rupture disc will burst and there will not be any impact for the other relief valves. After that it will open and there will not be any pop-up. Just is open up and it will go to the atmosphere or it will be collected in the drain. Okay, so in this case it will be collected in the drain pit. So this is this rupture disc, we don't know the value. So dimension we have 90 mm, and then you enter some weight, flange weight I am considering or not. Okay, but you need to refer the rupture disc data sheet to get the weight. After that, one flange is 80. Not okay. So we modeled up to here, and after that 165 is there. Overall dimension is up to this D, it is 165 That means up to this 165 So we need to subtract this with flange. Minus 80 plus 165. Okay. After that, this overall dimension, you see, it is 246. That includes this spool piece, reducer and flange. So we need to see the dimensions of the flange as well as the reducer in order to get the dimension of the spool. So what is the reducer is? Reducer size 3 inch by 1.5 inch. So go to Pipe Data Pro, go to Fittings, butt welded fittings. You select here concentric reducer 3 to 1.5 inch. So dimension is 89. So now we know the dimension of reducer is 89. Okay. You just remember 89 is the dimension of reducer. Then the line size has been changed to 1.5 inch. So your flange is 1.5 inch flange. What we need to do, go to the Pipe Data, again go to Pipe Data Pro, and you need to check 1.5 inch flange. Here you see 1.5 inch flange, well neck flange only. Okay, and it is 300 rating. Go to flange 16.5, 1.5 inch. Dimension is 69, 1.5 inch, 300 rating. And dimension is, and schedule you can change it to 10s. Okay, the dimension is 69. So we know the dimension of reducer is 89 plus this 69, 158. So we'll get to the overall weight, overall dimension is 158. Okay, overall dimension from this pole to flange is 246. So minus 246. Okay, so 88 is the dimension of this spool. So we enter 88, 88 here. Then go to the next element. You have to define the reducer. So we know the reducer dimension is 89. You enter 89 here. So in reducer, two types of reducer are there. I mean, one is concentric and one is eccentric. In this case, we are going to use concentric reducer. If it is any horizontal lines or any control hole session, you will get the eccentric reducer, and also at the pump suction lines, you will get the horizontal pumps, you will get the eccentric reducer, or on the pipe rack, you will use eccentric reducer. Okay. So now we know the dimension of reducer, that is 89 mm. Select reducer here, and you have to give the next dimension, that is smaller dimension, 1.5 size, sorry, smaller diameter, 1.5 inches. Next one, you need to enter the thickness of 1.5 inch. So 1.5 inch is 10s only, same 10s you have to use, 10s. So don't give any alpha value, just leave it. CAESAR will take the default value. So no need to provide any alpha value here. Okay. Go to help, you will get what is meant by alpha. What does alpha stands for? Okay. Okay. This is the angle of this one. Alpha is nothing but the angle. Okay. So up to here we model. Then we have to model the flange. Go to the next element. So if you go to the next element, you see the diameter is automatically getting changed. We didn't change anything because since we have defined the diameter 2 here, it will automatically change to that diameter. You have to be very correct. Okay. So here our dimension is 69 mm. Flange dimension is 69 mm. Enter the 69 mm here. Okay, and then weight. Weight you have to enter this flange weight. 2.991 plus 1.37. So that is 4.28. 4.28 into 10. You'll get the flange. Okay, so after this, you see there is a change in spec. Maybe the rating has been changed. It is 300 only. Still here it is 300. After that 150 rating, and their spec has been changed. You see, and their line number also will be changed. Now we need to check the dimensions of the PS, relief wall or PSV, anything. The vertical dimension is 124. So you have to refer the PSV data sheet for this. So in every project you will have PSV data sheet. Okay. For this project we don't have, so that's why I will show you the a reference PSV data sheet from other project. So this is from other project. Yeah, this is a typical PSV data sheet. So in PSV data sheet, you will have the horizontal as well as a vertical dimension. You see, the vertical dimension is 552 mm and your horizontal is 139 mm. Okay. So you need to model accordingly. So this is the inlet. Sorry. This is the outlet, I think so. Oh, yeah. So your dimension is 104 mm, not this height, this height. 104.8 and 139.7. So 1.5 inch to 2 inch. This line size is, you see, inlet is 1.5 inch and outlet is 2 inch. So inlet will have more pressure, you see 900 rating, and outlet will have lesser pressure. And because of the size, you see. And weight, yeah, weight is very important. I thought of checking the weight one. So you see, weight it is given as 43.1 kg. That is for whole assembly weight. What we need to do, if you are going to model something, now we'll take the same dimension and weight. Okay, but dimension will take it from the isometric and weight from that particular data sheet. The dimension is, here they have not mentioned the horizontal dimension, 124 they have given vertical dimension, and this dimension also will consider the same. So 124, that is a vertical dimension. Go to the next node, 124, and you enter the weight. This weight it is given as 43.1 kg. So 43.1 into 9.81. 422 or 423, you consider as 423, whole assembly weight 423 Newton. So you divide this one by 2. Equally you can split, and you provide the value. That is 211.5. 211.5. Okay, equally you can divide and enter the value. And this dimension, where this valve is going, line is going, is in, I'll copy this. It is going in minus x direction. Okay. Go to the next element. In minus x direction, minus 124, same dimensions we are given. And weight is, what is the weight? 211.5. So, weight we need to enter is 211.5. Okay. So up to here we have modeled. Okay. So after this there is a spec break. You see the spec has been changed to 11440 and line number also will be changed. We need to model from here onwards in a different spec. You see it is continuing on sheet 14. We'll go to sheet 14. Okay. This is, what is it? This is sheet 10. Okay. This is sheet 10. So you have to go to sheet 14 where the PSV is. This is sheet 11. Yeah, this is that one. Okay. So this is from here only it is getting continued from sheet 10. So here what is the line number you need to check? Here the line number has been changed to B 3 inch B721391140. So you go to the next element, you change the line number to 3 inch B72139. hyphen 114440. This is your spec. Okay. And then what is the dimension? It is, you see. So the PSV size is 2 inch, 1.5 by 2 inch. So the outlet you need to change this one as 2 inch. At this you see it is 1.5 inch. This is 1.5 inch and this is 2 inch. So you need to change this outlet as 2 inch. Okay. And 2 inch, what is the schedule? schedule 80. Okay, the outlet it is schedule 80. Okay, so from here onwards you have to change. I think from here it is 150, so no need to change this one. You can leave like that. The size has to be changed, and your material and all no need to change, because they are using the same material. From here only this one change, so no need to change this one. It will be 10s only. Okay, the line size only to be changed. And go to the next element. So here on flange is there, that flange is 2 inch. You see 2 inch flange is there, that is 150 rating only. You need to check 2 inch 150 rating flange. The dimension is 64 mm. Weight is approximately 2.46 plus 0.77, 32, 64. So enter in the minus x direction 64, and rigid, enter the rigid as 32.3. 32.3. So this is the line size. You see, if you check the line size, diameter, from here onwards it is 2 inch, because the PSV outlet is, inlet is 1.5 inch and outlet is 2 inch. So this is a this is a simple example. And you can see the material and all, everything is given. So this is different. Yeah, I see. 1.5 inch to 2 inch. Okay. So now we have modeled up to here. Again, one reducer is there, and from here onwards, we have modeled the flange here. So you have to change this line number. Already I copied that line number. Okay, from here. So you need to see this B72139, the line list. B72139. You see, this is that line. You need to check all the parameters. You see temperature 82 and 5, that is remains same only. Maximum and minimum design is same, and operating temperature will remain same. Fluid density also remains same. So if everything remains same, it's okay. Okay. If any changes over there, and only generally outlet will have lesser pressure. So we will check the design pressure here. This is working condition, and this is design condition. You see, main thing is pressure has been changed to 700 kilopascal. This one you have to change. Okay. So other things remain same. Only pressure you have to change it to 700. Accordingly, your hydro pressure also will change. So you need to see. Your hydro pressure is test pressure is 72730. You need to change 2730 from this flange onwards. Okay, don't change from here to here. From this flange onwards. This insulation and all I given just for a reference only. So Don't consider here. And fluid density, if it is remains same, you can take. No, not an issue. Okay, outlet. Okay, so this is okay. You save this one and go to the. We will continue with the modeling. And then reducer is a 3/2 reducer. You go to the fittings, butt-welded fittings, 3/2 reducer. So if main size, based on the main size only, the dimension of the reducer will change. If 3 inch is there, means 89 only. If it is 4 inch means, then it will change. Okay, so 3 inch only you need to, 3 inch 89 only. The dimension remains is 89. Go to the next node, minus 89. Yeah, from here onwards, here this flange, you need to see the material and all. Yes, material has been changed, no, from here. Material is A106 grade B and schedule 80. So you need to change the material from here onwards. 106 grade B, A106, and your thickness is schedule 80. Okay, so this is very important thing. Then your reducer. So a reducer, you select this, and your next diameter is 2 inch, correct, no? Yeah, sorry, 3 inch. This is 2 inch, sorry. So from 2 inch to 3 inch, 3 inch schedule 80. Not 980, 80. And then here they use only concentric reducer, no eccentric reducer. Okay, go to the next element. If you go to the next element, your line size automatically will get changed. See, the line has been changed, line size has been changed. And your corrosion allowance also, since this is a carbon steel, you change the corrosion allowance to 1 mm from here onwards. Okay. And then after that, 147 mm is the 147 plus 300 mm is there. It is going in minus x direction. Minus 147 minus 300. So at 300 you have one support. Just give plus y. And then again after that 400 mm is it is going, it is traveling in the same direction. Sorry, 3760. 3760 to 3790. It is going in minus z, minus x direction, that is 400. Bend is the. After that, it is getting dropped. You see, so I have to check the flange. 150 rating only. 3 inch 150 rating flange. Flanges 16.5. 3 inch 150 rating. The dimension is 70 mm. Okay. So the line is dropping 1178. It is going in negative y direction. Minus 1178 plus the flange dimension is 70. I am subtracting that one. It's a line is getting dropped. After that, you need to model the flange. This flange and valve and flange. Okay. The flange weight is approximately, you have to consider 4.64, 0.79, 540, 54 or 55 I will consider. The weight will be 55. Okay, minus 70, 55. And then minus this dimension, 209. 209 and you have to check the valve weight in the pipelet of row. Just I am giving some weight 500 approximately. You see, I have given wrongly the dimension, you see, in the positive direction. So it will be appearing like this, okay? You have to enter, you have to give carefully minus in the minus direction. Again, minus 70. You have to enter some weight, 32 something. Sorry, it's 55. Okay. Then 184 mm, sir. Let us subtract that value of flange. So minus 184 plus 70. And then bendezer, select, double click the bend, and it is moving towards which direction? It is moving towards in minus z direction. You see, it is moving towards in minus z direction. So what is the dimension? 570. Go to the next element, minus 570, and you have a T. Here you have a T. It is equal T only. Give welding T. So after this line is dropping at 172, minus 172. So what we need to do, we will check, because this model I know completely, that's why I am saying. So you need to check. I will show you the other completed model. That's why you have to refer 3D model correctly before using anything. So here you see, here we have model like this. So now we have completed the modeling from here to here, and we have completed up to here. So it is the other PSV also the same dimension we need to follow. So instead of modeling this one, so to save the time, what we will do, we will copy and paste. It's okay. So if we copy and paste, then it will be easy for us. Up to here, we will copy and paste, and it will be easy. Okay, here you see it is given us 124, and this consider as 250. The valve dimension as 250 only. Okay. So what I need to do, what we are going to do, we will copy this one. Okay, from here. Sorry, here there is no T, I think. So it is not elbow, it's T only, no? Yeah, I think it is T. I have considered as elbow. So you delete this. So that's why your dimension shows wrongly. Okay. So from here, you select the node number from here. From 3070 to here. 3790. Copy the entire node and paste it this direction. Okay. 3072 3790. Go to this one, elements, 3072 3790, not 3810 3790. You see, should not select this one because again it will go to towards z direction, minus z direction. Now we are going to copy this, and you need to check this. You need to remember this node number, this T node number. The T node number is 3070. Okay. So now copy, block operation, select, duplicate at the end of the input, and 3070. No. So what I am going to give, new node number, I am going to start the series from 4000. So 4000, I am taking 4010 minus 3070, 940. So I am going to give node increment as 940. Understood, no? We need to start the new series for different line. Okay. So in order to get the value, so our start node number is 3070. So you subtract 4000 minus 3070, you will get 940, giving this as node increment. Now I am going to give OK. Please wait. It is taking some time to process. So what happens means, so while processing, if you select means it will get close. So again you need to do. So in CAESAR, you have to be very careful. You close this. So again go to the element, we'll see whether it has been copied or not. You see it has been copied. So the first node number, whatever we have done, it is correct only. So you need to change the first node number. Then only your pipe will appear here. Because this T we have defined as 3070. Here we have to define the T, welding T. So you need to change this node number as 3070. If you change that one, so you see it is in plus Z direction. 3070 in plus Z direction. So what we need to do, we need to change this to minus Z direction. These dimensions. Understood, no? Or you can mirror it. You can do mirror. Minus means it will go to that direction. Minus. Either way you can do. Okay, now you can see our model has been copied and it is coming here. And you have to check because on the right side you don't have, because you see there is a gap here. That means this dimension is wrong. You need to update the dimension as per the isometric drawings. Here you see there are no flanges in this direction. So the overall dimension is 200 mm only. So in this case what we need to do, we will delete this one. Control D, delete. And then next element, Control D, delete. So we know this element is 85. So balance 115. Because overall dimension is 200. And you need to change this from node number. Because your two node number is 4030. And then this should be your, if you select 4030, it automatically comes to the T push. Okay. So you have to be very much careful. And you see this line, it is getting connected here. Save this. Okay. And this line, it is getting connected to this one. But practically it is getting, it is connected here, but you need to check the node. This node number, T node number, what we have defined is 3810. Okay. Either you can change, you just delete this. So now we are going to continue model from this line only. That we will see later. Okay. So we are going to continue this one. The vertical dimension, sorry. The vertical direction, we are going to continue like this. You see, yeah, it is getting continued. No, so this continuation we'll do it later. This continuation up to here it is going and it is getting connected to some pit. You see, relief pit it is connected. That we will do it later. Okay. So here what we need to define, here bend is there. You delete this bend, because why bend has been appeared means here bend is there. We have copied this node number, no? So here bend is there. So you need to do it properly. So once you complete the copy option, you need to check properly. So here we need to, instead of bend, you select T, and this 4730, this node number has to be changed to 4730, because it is nowhere connected to this model, no? So if it has to be connected properly, this node number, two node number, and this node number should be same. Then only it will get connected. Okay. Okay, so like this only we need to model the PSVs or PRV or any relief wells. Okay. I will check how to provide the safety wall reaction forces, how to calculate, and what is the support arrangement required for the PSVs. I will tell you in the next class.